Okay, video 2. Now we're going to take not exactly the same vectors because the ones I drew were not really the A and B. I just gave you something to go off of. We're going to take the given A and B here in example 6, and we're going to perform the same operations, but now we're going to do it algebraically. This is much, much easier to do, at least in my opinion it is. So we're going to take 2A. Well, that just means multiply 2 times vector A. So let's go ahead and just create these. So 2 times vector A is going to be 2 times 3, which is 6. 2 times 1 is 2. 2 times 0 is 0. 620 is letter A there. In letter B, we want to do 1/2 of vector B. So again, it's just multiplying the half or distributing the half through. So it looks like we are going to get 1/2 of -1 is -1/2. 1/2 of 6 is 3. And 1/2 of -3 is -3/2. Whoops, wrong bracket notation there. There we go. All right, in letter C, we just want to do the negative of A. Well, that's just distributing a negative throughout A. So we're going to get -3, -1, -0. Just kidding, there's no such thing. All right, part D, A plus 3B. So now we want to take A and add 3 B's to it. So I'm going to take 3 and I'm going to add 3 times -1. So 3 plus 3 is 0. So, excuse me, 3 plus -3 is 0. And then we're going to take 1 and add 3 6's to it. So 1 plus 18 is 19. And then 0 plus 3 -3's is -9. And then the last one, we're going to take 2 A's and then we're going to subtract B or add a -B. So 2 times 3 is 6 plus, minus a -1. So it's really going to be 7. 2 times 1 is 2. Minus 6 is -4. And then 2 times 0 is still 0. Minus a -3 is +3. Okay, hopefully those were not too difficult to do. Now let's talk a little bit about the length of a vector and how we actually find the length of a vector if we're given the actual vector itself. Length of a vector is derived from the distance formula. If you think about it, we've got a change in x direction and a change of y direction, so it really all comes down to a triangle. So the change of x is like the one leg, the change of y is the other leg. If you take both of those, square them, add them together, take the square root, what you get is the distance formula. So one of the main things here, because that's probably the easy part, is the notation. Got this notation right here, which looks like an absolute value bar. When we are talking about vectors, it is actually what is the magnitude notation. So that single bar around the outside is the magnitude. Now, if you think about it, because a magnitude is a length, and a length can't be negative, it still kind of is an absolute value, but that's the notation for the magnitude. So it looks like an absolute value, it's actually the magnitude. So if we want to find the magnitude, it is literally just going to be squaring each one of the pieces, adding them together, and then taking the square root of the sum. That's it. It is literally a distance formula. So the idea is what we're doing is we're saying that the vector here in number 7, -137, we're saying that that it starts at the origin. We're just going to start it there because it's the easiest place to do it. So we don't have to worry about subtracting 0 and all that kind of stuff from it. So what we get here is the square root of -1 squared plus 3 squared plus 7 squared. So that's going to be, what is that, square root of 1 plus 9 plus 49 is 59. So square root of 59. Square root of 59 is the magnitude of A. Very simple to do. Just find the magnitude, square each piece, add them together, take the square root. Okay, something to note. The magnitude of A plus the magnitude of B does not equal the magnitude of A plus B. So you can't take necessarily the magnitude of A plus the magnitude of B separately and say that that's the same thing as adding the two together, getting a resultant vector, and then that's the same magnitude. That doesn't work. So the question is, why? Why does that not work? Well, what it's called the triangle inequality. Triangle inequality. And you might remember from when you first started learning about triangles that the triangle inequality says the sum of two sides of a triangle must exceed the length of the third. Must exceed the length of the third side. Okay, and hopefully you guys remember that from when you learned about triangles, but if not, let's see if it makes sense. So we're going to take, and I'll just say that this is vector A. It's not the same as what we were dealing with above. And then this one right here is vector B. If I were to add those two things together, because I went tip to tail, this one down here is vector A plus B. So if you were to take side A and you were to add it to side B, that must exceed the length of A plus B. Because if it doesn't, then you're not going to be able to form a triangle. If A and B aren't longer than the sum of A plus B, you won't be able to form a triangle. So the triangle inequality with vectors here actually states this, and I'm going to have to qualify one piece here. It says vector A, magnitude of vector A plus the magnitude of vector B must be greater than or equal to the magnitude of vector A plus B. Now you might ask yourself, well, wait a minute, you just said it has to be bigger than. In vectors, and I could be wrong about this, I'm not actually positive, but I am pretty sure, because this takes me back, this is really more of a linear algebra concept. I believe that the equal to symbol is there because technically you can have vectors A and B both be zero vectors, means there's actually no length. And if that's the case, and you take two zero vectors and add them together, you're going to get another zero vector. So in this case, it would actually be an equal to symbol. But in regular triangles, that can't happen. But the triangle inequality for vectors does have the equal to symbol. I believe that is only to account for the fact that vectors A and B both could be zero vectors of no length. But that is your triangle inequality. Ultimately, that might come up a little bit, but the main thing is know how to find the magnitude of a vector. Very simple to do. All right, now let's talk about what's called a unit vector. Just like when we do in trig stuff, unit circles, a unit circle is called a unit circle because it has a radius of 1. And in general, mathematics and sciences, when we talk about units, we're talking about something which is 1. So a unit vector is a vector with a magnitude or a length of 1. That's it. So the vector has to have a length of 1. So let's look at example 8. The vector 3, 4, is that a unit vector? Well, the easiest way to figure it out is just to find its magnitude. So let's find the magnitude of vector A. Well, the magnitude is going to be the square root of each component squared added together. So let's see, we're going to get the square root of 9 plus 16, which is the square root of 25, which is 5. So the magnitude of that vector is 5, so this is obviously not a unit vector. Let's look at vector in example 9. So let's take the magnitude of A. Well, we're going to take the square root. So 3/5 squared is 9 over 25. 4/5 squared is 16 over 25. So adding those two things together, we get the square root of 25/25. And of course, 25 over 25 is 1, so we get the square root of 1, which is 1. So of course, this one is a unit vector. It has a magnitude of 1. And I'm kind of hoping that you can start piecing together what you see there. What did I have to do to this 3, 4 vector to make it a unit vector? Well, I divided each, the 3 and the 4, by 5. What is 5? 5 happens to be the magnitude of the vector 3, 4, which really should make sense. If I want to take something and make it of a length 1, say I have a piece of wood that's 4 feet long. If I want to make that a length of 1, I would divide by its length. 4 divided by 4 makes it a length of 1. So that would give me the unit vector. So in this case, you just take the vector and you divide it by its magnitude. That's all you have to do to find a unit vector. So let's look at example 10. Example 10 wants us to take vector A, find a vector which is parallel to A that has a length of 1. Or in other words, find a unit vector, length of 1, which is parallel to A. Well, if I want something to be parallel to a vector, if I want something to be parallel, it must have the same direction. Okay, its angle that it makes with the x-axis must be identical. And then if I want to find something that has, it's a unit vector, the first thing I need to do is I need to find the magnitude of the original vector. If it's already a unit vector, then we're good. But this is not going to be a unit vector. So let's see, 6 squared plus 1 squared plus negative 3 squared. Was that 36 plus 1 more is 37 plus 9 more is 46. So this thing has a magnitude of the square root of 46. Well, how do I make vector A a unit vector then? Well, I'm going to divide it by its magnitude. Or, to make it a unit vector, and I'm going to call this U. As a matter of fact, let's change colors there. We're going to call this vector U. It's now a unit vector if I take and I divide every piece by square root of 46. Well, it's the same thing as multiplying the outside by 1 over root 46 times our vector 6, 1, negative 3. You can distribute it through and do 6 over root 46, 1 over root 46, negative 3 over root 46, or you can leave it factored out. Either way is perfectly fine. So what we have is, this is a scalar multiple of vector A. So the direction and the slope, so direction and slope are the same. And because I'm multiplying it by its by 1 over its magnitude, it is now a unit vector. All right, hopefully we're all good there. Let's go ahead and finish this off. We got 2 more examples to go. So in this next one, it says, let vector A be 2, 2, 6. We want to find a vector which is parallel to A, but this time we want it to have a length of 4. Not a unit vector. We want it to have a length of 4. The idea is relatively the same, however. So the first thing we want to do is we want to find the magnitude of A, because we do need to find out what the length is currently. So the magnitude is going to be 2 squared plus 2 squared plus 6 squared. So what is that? 4 plus 4 is 8, plus 36 is 44. So we've got the square root of 44. Does not simplify to a nice easy number. I mean, you could write it as 2 root 11 if you wanted to, but just for the sake of argument, that's approximately a length of 6.5. Definitely not a unit vector. We can, however, create a unit vector out of this. And you might say to yourself, why do I want to create a unit vector? Well, it's a good question. Let's go ahead and show that. The unit vector is going to be 1 over root 44 times the original vector 2, 2, 6. This now has a length or a magnitude of 1. Well, if now I have a vector which has a length of 1, how am I going to make it a length of 4? That should hopefully be pretty easy. If I want to take something of length 1 and make it any other length, I just multiply by whatever it is that I want to make it that length. So, therefore, to find my specific vector, I just take 4 and I multiply it by the unit vector, which now has a length of 4 and is parallel to the original vector. That's it. Obviously, that can be simplified. I could distribute the 4, I could factor out a 2, I can do all kinds of other stuff. It's perfectly fine the way it is. All right, and the last thing we're going to talk about is not really an example. It's just an idea that you kind of need to know because we're going to be using these symbols quite frequently. I, J, and K are what's known as the standard basis or the standard unit vectors in 3 dimensions. I is basically the vector 1, 0, 0. So if you think about that on an actual graph, it's just 1 unit out in the x direction. J is the standard unit vector in the y direction, 0, 1, 0. So it's 1 unit out in the y direction, and then K represents the unit vector in the z direction. The idea of this, and this is something you would definitely learn much more about in linear algebra, but a basis is using these 3 vectors. We can get anywhere in 3-dimensional space by doing some kind of a combination. So we can get anywhere in 3D space. And the last part about that is they are linearly independent. Yeah, I'm not going to go into depth as far as what linearly independent is. That is definitely a linear algebra concept. But this is ultimately what it means. If I wanted to get to the point 532 by using a vector, if I want to use I, J, and K, I could do that very easily because I could just say, okay, let's take 5 and multiply it times I, plus 3 and multiply it times J, plus 2 and multiply it times K. Well, I is the unit vector 1, 0, 0, so that's 5 times 1, 0, 0. 3 is the unit vector in the direction of I, so 0, 1, oops, make that a 1, 1, 0. And then K is the unit vector in the z direction. So now if I were to go ahead and multiply these out, I would get 5, 0, 0 plus 0, 3, 0 plus 0, 0, 2. And then I can add those 3 vectors together just by adding the components. And I would get the vector 5, 3, 2. And that vector would get me to the point 532 in 3-dimensional space. Obviously, you don't need to go through every single step that I just did there. If we wanted to write things in terms, if you see 5i plus 3j plus 2k, you can skip from there right down to there, and you'll know that that is exactly the same thing. It's the vector 532. All right, that's it. That is enough for this lesson. So you should be good.